appeared in the roster was in fact signed up for Blackboard. So you all should be. If you're not, let me know as soon as possible. The reason is, just to make sure you're really on there and you know how to use it, we are going to have our very first extra credit assignment tonight. It will go online right now, or actually about 10 o'clock, and it'll stay up until 11:30 this evening. At 11:30, it will disappear forever. You have 2 attempts at it. It will be 10 questions. They're a combination of short answer and multiple choice, and they will be based on chapters 1 and 2. Any questions? Yeah.
I go directly to work after this until midnight. Is there any chance it can be left open?
Midnight.
I usually do.
Oh my goodness. Okay. Send me an email. Okay. PLUICDU. And I'll see if I can somehow do something. Okay. All right. Anyway, so this is it. 2 attempts, and life can be complicated, can't it? This is the Triton Blackboard site. When you finally get there, the section that you want to click on, this is the home page for the organic. When you finally get there, you want to look at course materials. Course materials is a link that will take you to stuff. I mentioned the organic interactive. This is the thing for it. Lecture slides are there. I hope that you guys have printed those. And this is the extra credit. What you will do is you simply click on this thing. When you click on it, it will open. It will say, are you ready to begin? And you click the begin button. You will then get a sheet with 10 questions. You enter them. Make sure you hit submit when you're done. Okay? It also has options for save and come back later. In general, those don't always work. If you happen to be in Blackboard and you lose your internet connection, or you somehow just screw up and forget to click the submit, Blackboard will sometimes lock you out. Okay? That's not good. If that happens, please let me know as fast as you can. But as long as you remember to click your submit button and your internet doesn't go down, you should be okay. Any questions? There's the extra credit. Good luck. All right. We talked a little bit about how to make covalent bonds by sharing electrons. And from general chemistry, everyone remembers ionic compounds. In ionic compounds, you totally transfer electrons from one atom to another, make a pair of charged ions, and these are held together electrostatically. For a covalent compound like this, what you're doing is actually sharing the electrons between the two. Now, organic chemistry involves lots and lots of reactions. These reactions are going to occur mostly in compounds that contain covalent bonds. And what we wind up doing is breaking these covalent bonds. The reason that we can do this is that these 2 examples here really do represent limits in bonding. Let's look at 2 examples here. This is hydrogen, H2, and this is hydrogen fluoride, HF. When we have a covalent bond between 2 identical atoms, we're going to get sharing of electrons between them that's perfect and symmetrical. We can look at this using the electrostatic potential map. Now, we saw this back in chapter 1. We'll see them all during the semester. The electrostatic potential map is sort of like electron density, not exactly. For hydrogen, here's our H2 molecule. What we do is simply calculate where the electrons are, and we represent that as a surface. We then take the surface and we color it, and the color represents basically where the electrons are from one end of the molecule to the other. We have a nice, clean, uniform egg here for hydrogen. And what that tells us is that the electron density is essentially uniform along the covalent bond. Now, if we do the same exercise here for hydrogen fluoride, the potential map we get looks much, much different. We have one region of the molecule here, this very deep blue. When we color this thing, the computer uses blue to indicate the lack of electrons, low electron density. Likewise, red indicates very high electron density. The point here is that this bond is very highly polarized. The fluorine has drawn the electrons in the covalent bond here, away from the hydrogen, leaving it positive, and towards itself. Polar covalent bonds are the types of things that are going to undergo reaction in organic chemistry. Now, we can show this polarization using this little arrow thing. It's a dipole. And basically, you call it crossed arrow. And basically what it is just an arrow. You don't have to draw it with a gradient. It just looks cute. And you put a plus at one end. And what you do is you align this either to the molecule or the bond. And this indicates this end is positive and this end is negative. Now, the reason for all this simply is a phenomena called electronegativity. Should have covered this in general chemistry. Basically, electronegativity is a arbitrary numeric scale going from 0 to 4. And what it does is it ranks atoms in their ability to attract electrons towards themselves in a covalent bond. Okay? There's a general ramp here. Down in this corner of the periodic table, we have the lowest numbers. And up here with fluorine, we have the highest number. Basically, it goes from here up to here. As a rule of thumb, nobody ever remembers these numbers, you don't have to. But as a rule of thumb, what you can say is that as you go across any period, electronegativity values, these things, will increase. As you go up in any group, they also increase. So if you just want a relative thing, let's say we're looking at carbon and silicon. Carbon is higher than silicon in the periodic table, therefore it will be more electronegative. Any questions? Well, we did Lewis structures the other day. And this is obviously the Lewis structure of water. We also talked about the valence shell, valence electron, repulsion, whatever, Vesper. As we look at oxygen as the central atom here, according to the valence shell electron repulsion theory, we have 4 things attached around this oxygen. We have 2 hydrogens and we have 2 lone pairs. Remember, just like carbon, when you have 4 things attached around there, we're going to have tetrahedral geometry. Now, that's tetrahedral in terms of electron pair. As far as what we see here, we only have 2 hydrogens showing up. Therefore, the structure that we would draw and see would look like this. If we just look at the atoms, this guy is bent. And in fact, that's what we refer to this. This is bent geometry. All right, let's take this and let's apply electronegativities to water. If you look up in the table, hydrogen is about 2.1 and oxygen is 3.5. That means that oxygen is more electronegative. And because oxygen is more electronegative, this covalent bond is going to be polarized. And so is this one. We have 2 little dipoles looking like this. But because the molecular geometry here is bent, we have a resulting molecular dipole. The molecular dipole basically is going to say that this end of the molecule is positive and this end is negative. We would show it like this. If you're interested in physics, this is actually the vector sum of our 2 dipoles. Now we can render this as an electrostatic potential map. And as we look at this, we see just what we predict here. Down here by the hydrogens, we have a nice blue bottom. This is very positive. And up here by the oxygen, that's where the electrons are, that's negative. The fact that we have this molecular dipole in water is the thing that makes water so unique as a solvent. This can undergo, as we'll see in a bit, hydrogen bonding, and it can also, because it's so polar, interact well with polar molecules. This is also the basis for ionization of acids and bases. But okay, let's look at an organic molecule and do the same sort of thing. Here we have methanol. We have 1 carbon and an OH. This is an alcohol. It's the organic equivalent of water. Once again, electronegativities, 2.5 and 3.5. That means that the bond here, up and down, is going to be polarized. If we do the electrostatic potential map, again you can see the oxygen has drawn the electrons up away from the carbon and away from the hydrogen. Nice big red spot here. This, once again, is the origin of the chemistry of alcohols. They will have high electron density by the oxygen, and we'll see we can remove this hydrogen because this polarization makes this acidic. Any questions? All right, let's go one step further here, and let's address a concept called formal charge. This is something that we use a lot in organic chemistry because we deal with charged species. Usually these are intermediates, but it's very important to understand why we're saying that these are positive, these are negative, etc. One way to look at this is methanol, the molecule we just started with, right? Here we have a covalent bond between the carbon and the oxygen. We know that this really is 2 electrons in there, right? All right, if we have 2 electrons in there, what would happen if I took both of these electrons and simply gave them to the oxygen? If I did that, and again, here's my curvy arrow showing I've moved my electrons. electrons. I have an oxygen here with 2, 4, 6, and again 8 electrons, counting the bond there. And this carbon has 2, 4, 6 total, right? But the electron that we took off of our carbon came into this Lewis diagram with 4 electrons, didn't it? It shared them with oxygen and with hydrogen. And when we remove this electron, we are now missing one. Therefore, we would say that this carbon must be positive. Just as a rule of thumb, when you have a carbon that's only bonded to 3 things, it is going to be positive. We took this extra electron and gave it to the oxygen. That means it now has 1 extra electron. And so likewise, the oxygen must be, oops, sorry, there it came, by itself, must be negative. So we've broken a covalent bond here, and we've made a pair of ions. Rule of thumb, carbon with 3 things is going to be positive. Oxygen with 3 pairs, unshared pairs of electrons, is always going to be negative. Now, there's another way to calculate formal charge without having to break bonds. It's a very simple little formula. Formal charge. We're going to look at the atom, going to find a periodic table, and see what group it's in. That's group 1 through 8. Then we're going to look and see how many bonding electrons we have, and how many unshared pairs of electrons we have. The formula simply takes group, half the bonding, subtract all the unshared, and you see what number you wind up with. For carbon here, carbon is group 4. We have 2, 4, 6 bonding electrons. So we're going to take 3 off of that. We have no unshared pairs. 4 minus 3 plus 1 is our formal charge. Very simple little exercise. Again, you can just remember the thing. Carbon with 3 bonds is always going to be positive. Or you can use this little formula. And it is worth knowing this little formula because you will see it on exams, quizzes, and whatever. Speaking of that, we do have exams, right? Everyone realizes that. Everyone remembers. 3 of them. And a final. There are things that you have to remember in organic chemistry. And nobody likes to remember. Okay? So, what I allow you to do is to bring 1 3x5 card to the exam with anything on it that you like. Remember how I said using the mini prints teaches you to write small? This is an example of when it's very useful to know how to write.
Only one-sided?
Usually I do only one side. For the first exam, we can do 2 sides if you want, and then work our way up. Or down, whatever. Hydrogen, let's just do this. Hydrogen is group 1. We have 2 electrons here, so we're going to subtract 1 from it. Hydrogens here have a charge of 0. This is trimethylamine and oxide. How about you calculate the formal charge for the nitrogen and the oxygen? All right. Formal charge for our nitrogen and our oxygen. We look at our periodic table and we find nitrogen. Nitrogen is here in group 5A. We have 2, 4, 6, 8. So we're going to subtract 4 electrons from that. We have no unshared pairs. Our nitrogen is a +1. The oxygen. Oxygen lives in group 6. We have 2 electrons in covalent bonds, so we're going to subtract 1 of those. Then we're going to subtract 1, 2, 3, 4, 5, 6 from that. Oxygen is a -1.
Couldn't you just look at the nitrogen and then see the bonds?
Exactly. You can do this in your head. Like we said, a carbon with 3 things attached
You know,
is going to be positive. Nitrogen with 4 things attached is going to be positive. Oxygen with 1 thing is going to be negative. So you can use the formula or you can use your head. Now that works unless you have something like this. This is azide anion. Let's do the nitrogens in azide anion. Well, nitrogen still lives in group 5, doesn't it? Here we have, so we're going to start with 5. We're going to subtract 1, 2, 3, 4, 5, 6. That nitrogen is -1. The guy in the middle. Now this one we could guess because we have nice 4 bonds to our nitrogen. But we're at group 5. We subtract 1, 2, 3, 4. This is +1. And this nitrogen, well, it's just like this one, isn't it? We have group 5 -1, 2, 3, 4, 5, 6. Once again, this is -1. Any question?
So that wouldn't have like a dipole.
No, this does not. This is a linear molecule, and we will have equal charge distribution. Now, we will talk about resonance today. We can draw azide anion a different way. We can draw it this way. This is called a resonance form. Again, we'll talk about those in a minute. But look at this, and once again come up with formal charges for our nitrogens.
you call it a resonance form?
Yep, called a resonance form. We're going to do resonance in just a second. Well, nitrogen's at group 5. We're going to subtract 1, 2, 3, 4, 5, 6, 7, making that a -2. Our nitrogen in the middle has 4 bonds. We therefore expect this to be +1. Group 5 -1, 2, 3, 4. My gosh, it is +1. And the nitrogen on the end. We're at group 5, aren't we? Subtract 1, 2, 3, 4, 5. That's a 0.
So resonance structure is just changing the number of bonds
It changes.
instead of the
When we do
formal charge.
resonance, we're going to move electrons between adjacent sp and sp² centers, basically. without moving atoms, just electrons. Resonance is going to be very, very important to organic chemistry because it will describe to us in a very physical way electron distribution, and therefore we can predict reactivity. But let's get to that in just 1 second. Here's our summary. As I said, if we have a carbon with 3 things attached, this is going to be a +1. Now, this is called a carbon radical. It only has 1 electron. Because it only has 1 unpaired electron here, not 2, this, well, let's do our formal charge. This is group 4, -1, 2, 3, 4. This is a 0. This is a carbanion, it's called. This is a carbocation, carbanion. Here we have group 4, -1, 2, 3, 4, 5, and that's -1. Nitrogen with 4 things is a +1. Oxygen with 3 things is a +1. Oxygen with 1 thing is a -1, and sulfur is just like oxygen. So those are just things you can remember by inspection. All right. In order to develop resonance, our discussion of resonance, I'd like to start with a very simple Lewis problem. Come on. I said all that. Well, listen to what I said. Now, let's start by doing like we did back in chapter 1, and let's draw a Lewis structure for the nitrate anion. Now, this isn't difficult. Remember, this is just what we did. Step 1, we find the atoms in the periodic table. Once we know the atoms in the periodic table, we look at their group numbers. Nitrogen, group 5, 5 valence electrons. Each oxygen will have 6 valence electrons. Let's also remember we have a negative charge on the whole complex. So, this is what we start with. Nitrogen with 5, and 3 oxygens with 6. We need to arrange these things in such a way that we can make nice, happy covalent bonds with 2 electrons. And we also want to give everything an octet. As we look at these, maybe the first thing to do is to take these the way I've drawn them on the oxygen, and let's just move them up, get them out of the way. Now if I do that, here we have a pair of electrons we can use to make a covalent bond here. So that's good. That's a nice simple thing. That's good. Here we have 6 electrons, here we have 6 electrons, here we only have 1. But remember, we do have a negative charge on this species. So we're going to take this negative charge, that's our extra electron, and we're going to put it on our nitrogen. I'm going to put it right here. Now this group of atoms has a net negative charge. Clearly, I can make another covalent bond here.
Wait, can you repeat where the extra electron came from?
I'm sorry?
Can you repeat where the extra electron
Where it came? Well, this is nitrate anion.
Oh,
So by definition, it has 1 extra electron. All right. In order to make a bond here, I'm going to have to move this lone pair of electrons from the top of the nitrogen in so I can make this bond right here. Again, We show this with a curvy arrow. Now we're set to make 3 covalent bonds. However, our poor nitrogen is sitting here in the middle, and it only has 6 electrons. That's going to make our nitrogen unhappy, isn't it? Therefore, I'm going to take and grab 1 pair of electrons. Well, nitrogen here is with 6. That's not good. So what I'm going to do is take one of the pairs from an adjacent oxygen, and I'm going to move them in, like this. Now we're going to have 2 electron pairs in between. Everybody now has 8. 8 on the nitrogen and 8 on all the oxygens. So we can say that this is the structure then for nitrate. However, I hope that what I've done here sounds a bit arbitrary to you. When we were stuck with not enough electrons on the nitrogen, I grabbed them from this oxygen and moved them in, didn't I? Why did I choose that oxygen and not this one or this one?
No reason.
No reason. It was totally arbitrary, wasn't it? I could take the electrons from this guy, move them in to make a double bond, and put these back where they came from. I would show it with curvy arrows this way. I now have this structure. Likewise, I could take the electrons from the guy on the bottom. I could move them up and put these back where they came from. And I could draw this structure.
Does it have any effect on the stereochemistry of the compound?
Nope, nope, we'll see that. Okay, so we have 3 potential structures. They all look different. They all have different arrangements of electrons. And the simple question is, well, what's right? Which is it? You gotta have one. Well, in fact, these are all identical structures. All we have done is rearrange the electrons arbitrarily. We've done this through adjacent sp² centers. Only thing we've moved are electrons. We can do that between adjacent centers because remember, Lewis structures are just bookkeeping anyway. What we did is we started with this. We took electrons from the oxygen, moved them in, moved these over. And we made this. Took electrons from the bottom, moved them up, moved them over. And we made this. These are examples of what we will call resonance forms. Again, the arbitrary placement of electrons between adjacent sp and sp² centers. What does the thing really look like? Well, I think I just had this slide. It's a hybrid. It's a hybrid of all of these structures put together. I also want to point out here that we have a very special arrow that we use when we link resonance forms. It's a double-headed arrow. Now this isn't the equilibrium arrow. Equilibrium is 2 arrows. Only time you'll ever use a double-headed arrow is when you're drawing resonance forms. The hybrid, we kind of draw something like this. We say what we have is a nitrogen with 1 bond, 1 full bond between all of the oxygens, and we have partial bonding as well. The whole thing, again, as a net negative charge. If you do the electrostatic potential map, and of course correct for the geometry, think about the geometry. Nitrogen with three things attached is trigonal, isn't it? This is perfect charge distribution around all the oxygens. This is the resonance hybrid. It doesn't flip back and forth from one to the other, to the other, to the other. That's the way we do it in order to understand how this hybrid is constructed. But the molecule exists only as the hybrid. All right, there are rules for drawing resonance forms. Most important here, we're going to move only electrons. We never move atoms. Every structure that you come up with must be a legal Lewis structure. Again, we're going to go between adjacent sp and sp squared centers and heteroatoms. And it's important that you remember that these are limits. When we draw something with charges on one end of the molecule and the other, that's like a mathematical limit. You never get there. It never ever looks that way. But you can use this as a gauge, visual gauge, for where electron density is going to be in a molecule. When we do carbonyl condensation reactions, we'll see that that's very important. All right, the king of resonance in organic chemistry is benzene. Benzene, well, we had a real rough time back in the 1870s trying to figure out what benzene was. Everybody knew it was C6H6. And this is one of the structures that you could draw. This turns out to be the correct one. But the problem with this is that this structure has carbon-carbon double bonds. Carbon-carbon double bonds undergo characteristic reactions. They have a characteristic reactivity. Benzene didn't. It didn't do any of the things it was supposed to do. And so people said, well, it can't be this. A gentleman named Kekulé, organic chemist of the time, the story goes, he was sitting by the fire, sipping scotch, fell asleep, and had a dream. And in the dream, it came to him exactly what was happening. In this dream hallucination, a snake was mocking him, and the snake reached around, grabbed its tail, and started spinning madly in front of him. He woke up and said, I've got it. Well, what he had was basically this. Let's redraw our benzene this way, as a line drawing. Remember, each of these vertex has a hydrogen attached, just like that, but we're not going to show them. Now what Kekulé did was, he took benzene and he said, just like my snake, I could take and move these electrons from here down to here. Now that would put too many electrons, too many bonds here, wouldn't it? So I got to move these over to here. And that puts too many here, so I got to move this up to there. And when I do, I get this structure. Now, Kekulé imagined that benzene was, in fact, bouncing back and forth between these very, very quickly. That the electrons were spinning around just like this snake. He was wrong, but still, he did manage to explain the structure and the lack of reactivity of benzene. It's not a carbon-carbon double bond. It's a mixture of these two. Today we represent it differently. Every carbon atom in benzene has one p orbital, doesn't it? It's an sp squared carbon. All these p orbitals in this ring line up, top and bottom. Very nice looking array. When they line up like this, they overlap. And they form this. This is the electrostatic potential map for benzene. And you'll see that above and below the plane, we have this huge red spot. That's where all these electrons are living. The reactions of benzene begin at our big red spot here. Not a carbon-carbon double bond. It's totally different. Another representation are two calculiforms, and they're called calculiforms. And this is the electrostatic potential map, and I've overlaid the molecule here. Any questions?
So the carbon-carbon double bond is an sp, and then the carbon-carbon single
No, they're
bond
all
is
sp squared.
They're all
but
sp squared.
They do not overlap into a simple double bond. If you want to think about it, each of these is 1.5 bonds. One way to think about it. Another example that we use a lot in organic chemistry is a carboxylate anion. This is one resonance structure. We can take the electrons from the oxygen, move in to make a double bond. As we do, we have to move these out on this oxygen, wind up with our negative charge here, and the hybrid looks like this.
So you're saying that because of how it's structured, it makes it more stable?
Absolutely. Benzene is an incredibly stable compound. Now, my favorite challenge in all of organic chemistry is this guy, tropylium ion. This is a 7-membered ring. Everyone should now draw a 7-membered ring for me. It's not that easy. And this is a positive ion. We know that because the total charge here, carbon with 3 things, is +1. Tropylium is an incredibly stable cation. Carbocations are very, very reactive. Tropylium is so stable you can dissolve it in water. The reason that it's so stable is that this positive charge can be delocalized by resonance.
You can or you can't dissolve it all?
Oh, it can.
Okay.
And most carbocations would react instantly with water. Lifetime of a carbocation, I actually measured this, is about 10 to the -9 seconds. Okay? Very, very reactive. Tropylium, if we start with something like this, we can move electrons this way, move our positive charge from here down to here. Do it again. Positive charge is now here. Do it again. And again. And again. And finally, one more time. If you're counting here, we have placed this positive charge on all 7 carbon atoms. That means we have delocalized this positive charge over every member of this ring. We show this as a delta plus. We use the little delta, Greek delta. Somehow Microsoft turned these into D's, but imagine that they're deltas. Delta indicates partially. Each of these has 1/7 of a positive charge. The electrostatic potential map here is gorgeous. This is what we start with, See, these are deltas. Electrostatic potential map looks like this. Again, the positive charge uniformly over all atoms. Any questions? All right, I said that we were going to use resonance in organic to rationalize and predict reactivity. Here's an example of what I mean by that. This is the acetone anion. It's an anion on the alpha carbonyl, or the alpha carbon, the carbon adjacent to a carbon-oxygen double bond. This can be written in another resonance form. Quickly jot it down. Not going to push the button yet, but I'll talk. What we're going to do is we're going to take the electron pair. We're going to move it from here in to make a double bond. Now when we do that, that would put 5 bonds on this carbon. You can't do that. Therefore, we have to take one of these, move it up to the oxygen. So we want to show 2 movements in our resonance diagram. Move the electrons in, move the electrons up. And we wind up with this as our structure. When we do carbonyl condensation reactions, that will be next semester, we will actually use this carbanion as a nucleophile. This will be the center for bond making and bond breaking. And we know that this has partial negative charge because it's a hybrid of these 2 resonance forms. Quickly, this is the butane dione anion. You can do 2 resonance forms. Quickly draw them. On exams, I can assure you on exam 1, I will ask you to draw resonance forms. Make sure that you can do this little operation.
Do you put your line over the C? Is that just showing that you're removing the bond?
Right, this is the negative charge.
Oh, that's the name, okay.
Yeah, that indicates it's a negative charge. What we want to do is to take our electron pair, just like we did here, move it in. We will take and move the electrons from our carbon-oxygen double bond, move them up, and we'll wind up with this as one resonance form. Now for a second resonance form, we could take these electrons from this oxygen, we could put them back and make a carbon-oxygen double bond quickly. But if we did that, we've got a double bond here. We have to do something with that. We could move these electrons from here to here, moving these up to the oxygen. And we could have this as our other resonance form. So the 3 major resonance forms of 1,2-butane dione will be this, this, and this. The prediction is the central carbon here will have carbanion character. That's how we use resonance in organic chemistry. Now, the little sheet that I gave you, this thing, some of you came in late, you didn't get one. If you don't, come get one. On the back, the last two problems, I think, are resonance problems. Why don't you do that quickly while you're thinking about it, and in a couple minutes.
Earlier, so that not didn't confuse on the skeletal structure, so it did bone structure.
Okay. And then we're going to go do, and then we'll talk about all of the answers. Let's go back to what we were saying about water. Acids and bases are going to begin and end with water. We talked about water as a polar molecule. Again, it is polar because we have differences in electronegativity along our covalent bonds. These are polarized covalent bonds. We wind up with a net molecular dipole looking something like this. Electrostatic potential map, same sort of thing. Nice big positive area, nice big negative area. The fact that water has this great dipole is the thing that allows it to dissolve things like ionic compounds. It's also the thing that's going to allow it to ionize acids and bases. When we speak about things dissolving in water, remember a solution, technically, is what's referred to as a homogeneous mixture. That means any sample you take from it is going to have the same composition, even though it is simple a mixture. And that is, of course, what we mean by solution. The thing that lets water do this is the fact that we have this magnificent dipole. But there's also limits to things that can dissolve in water. We have just a little bit of nomenclature we need to make sure we remember. This is alcohol being poured into water. Alcohol, ethyl alcohol, this is the structure, has an OH group, just like water does. That makes it polar. Because it's polar, it interacts very well with the molecular dipole of water. Rule of thumb is that like dissolves like. What that really means is water is a polar solvent. It will dissolve polar compounds. Things that dissolve in water are called hydrophilic. Water-loving, hydrophilic. If something is hydrophilic, basically that means it's polar and it will dissolve in water. The opposite is something like olive oil being dribbled into water. Olive oil, this is a simple hydrocarbon. Hydrocarbon bonds are not polar at all. And because they're not polar at all, they cannot interact well with water, which is very polar. Therefore, you get globules formed instead of a solution. This is referred to as hydrophobic, water-fearing. Most organic compounds are going to be hydrophobic. Many of them will have part of them that is hydrophobic, part that is hydrophilic, and they'll form special organized structures in solution. That's where membranes come from in biochemistry. All right, so just make sure that you understand the concept and whatever. Another feature about water. We said that water has this magnificent dipole. If you think about it, there's a hydrogen here and a hydrogen here, isn't it? And a nice big oxygen there. If water is capable of interacting with polar things, it only makes sense that it can interact with itself as well. That means if I took another water and I brought it up next to it, I could form a complex with the negative end of one water interacting with the positive end of another. This is referred to as a hydrogen bond. Now in water, I could do this again. Put another one here, and now I have two hydrogen bonds. I could do this again. Take it, tip it like this, hydrogen, oxygen, I now have three hydrogen bonds. Water can do this in an indefinite organized structure. This is one water with 4 hydrogens or 4 waters around it, all of these hydrogen bonding. But you know, this sort of representation doesn't really show you what's going on. If you look at this model here, this is a computer rendering of a complex of water. And the thing I like to point out here is look at these guys. So this is somebody's hydrogen, and it's essentially totally swallowed by this adjacent oxygen, isn't it? This isn't just sitting here pointing at each other. These are very significant interactions between all of these molecules. It is this hydrogen bonding ability that makes water once again unique. It is the substance that is the best possible hydrogen bonder that we know of. This will affect boiling point, etc. It's a kind of a very important feature of water in general. We've all heard of hydrogen bonding. In biology, we talk about it in terms of nucleic acids. This is a GC pair. We have up here an NH, and we have an oxygen. We can take electrons from the oxygen, interact with our NH here. Again, here's an NH and a nitrogen. We have lone pairs here. Another interaction, and another NH oxygen going this way. We can have 3 matched hydrogen bonds in this pair of DNA bases. We all know that these organize in such a way where we have AT and GC pairs in our nucleic acid. I will point out that as you look at this, we have charged phosphates here on the outside, don't we? And these guys are all in the middle. The only reason that DNA and RNA can bind together and form hydrogen bonding complexes is that these guys are shielded from the water. If you look at a space-filling model, there's no space here in the middle for water, is there? That means that this type of hydrogen bonding can occur. If these things were open to the water, there's no way in the world that these would hydrogen bond with each other as opposed to hydrogen bond with water. Water is just so darn good at it. All right, well, there's one other feature of this hydrogen bonding that's very, very important. If we take 2 waters sitting here next to each other, just hydrogen bonding away, as we saw in the previous slide, this is a really significant interaction, isn't it? One is swallowing half of the other. All it takes is a little tiny nudge, a little bump, a little bit of energy, and suddenly this hydrogen moves from one to the other. We have made hydronium ion and hydroxide. Now these are still sitting next to each other. You can hand it back, and we're back to 2 waters. We could sit and do this all day. In fact, water does this all day. This is the autoionization, or the autoprotolysis of water. This equilibrium goes on constantly. In pure water at 25 degrees, concentration of hydronium and hydroxide, this guy and this guy, is 10 to the minus 7 molar. Remember, this is where pH of 7 comes from. Pure water, hydronium ion concentration is always 10 to the minus 7 molar. Let's just look at one cute feature of all this. As we have made this pair of ions, we have some very impressive looking ions. This is the hydronium, this is hydroxide, huge negative charge, huge positive charge. The only reason that this works is that water is able to take these charges and stabilize them. It stabilizes them by dispersing the charge to neighboring waters. Here's hydronium. Here's what it looks like from the top. On the side, you can see very clearly our huge blue bottom. Now, this doesn't just exist by itself. This exists in water. So we're going to take this positive species and we're going to surround it by, at first I'm just going to put 3 waters. Then I'm going to use my magic computer to calculate charge distribution. So we're starting here with our hydronium ion in the middle, great big blue ball. And I'm going to now calculate the charge distribution over the entire complex of 4 waters. When I do that, I wind up with something like this. You see that our big blue ball has gone away. We're left with something that's greenish, but it's sure better than our blue ball was. This is a more realistic version of water. We have a hydronium, and we have 8 waters around it. We can do exactly the same calculation here. We're starting with our big blue ball in the middle. Here you can see how big it is on the bottom. We calculate charge distribution over the whole complex. Our blue ball is not only gone, don't you hate that? Our big blue ball is not only gone, but here we have a nice red peak where our hydronium ion used to live. Here's the hydronium ion. As you see, it is gone, and it's now even a red peak. So water can support this ionization because it's just so good at stabilizing these charges. All right. Let's look at a polar covalent bond in water. Just like we saw with water, something like hydrogen fluoride. This again is very highly polarized. Here's our hydrogen, there's our fluorine. If we take HF and we put it in water, by the same mechanism that we used before, water is capable of splitting this covalent bond, breaking it into hydronium and fluoride. Looks kind of like this for hydrogen bonding. Once again, a tiny bit of energy. This pops over. We now have our pair of ions. This is the ionization of an acid in water. The driving force is that water is capable of stabilizing these ions. Now, in general chemistry, you represented this as an equilibrium. In the equilibrium, we have a forward reaction, a reverse reaction. This is the equilibrium reaction with our two arrows, not a double-headed arrow, two arrows. And this is the equilibrium ionization of an acid in water. When we talk about acids, we're going to talk about two categories, strong acids and weak acids. That simply is going to be a descriptive term for this equilibrium. If we have a strong acid, that means that the reaction goes favorably in the forward direction. We have lots and lots of hydronium. If we have a weak acid, reaction goes backward, it's more favorable. We have very little hydronium and lots of this. Organic acids are going to be weak acids. Things like HCl, nitric acid, whatever, those are strong acids. Those are 100% ionized. Weak acids, very, very slightly ionized. In the Bronsted acid-base theory, we can describe acids and bases very simply. Anything that donates a proton is a Bronsted acid. Anything that accepts a proton, in this case it's water, is a Bronsted base. Very, very simple. Bronsted acid donates, Bronsted base accepts. Strong acid, 100% ionization. Weak acid, very slight. Let's just look at some strong acids here. HCl, 100% ionization. This is nitric acid. In nitric acid, we're going to pull off this OH. This is our polar bond that we pull it off. This is perchloric acid. Again, polar bond, we yank this off. These guys are called monoprotic because you only transfer one proton. We can also have diprotic acids. Sulfuric acid is the classic example here. We have two OHs. Both of these are polar bonds. Both of these hydrogens are yanked off. And again, this is called a diprotic acid. It comes off one at a time, hydrogen sulfate, and then sulfate. Any questions? You also learned in general chemistry about the acid dissociation constant. This is important to know for organic because when we speak of things like, the acetone anion, we're going to be talking about its pKa. So let's just review what we mean by that. The law of mass action basically says we can write an equilibrium constant for an ionization such as this. Equilibrium constant is basically products divided by reactants, and we're going to raise each of these to the stoichiometric power that's in the balanced equation. Now that's a lot, that was general chemistry, whatever. But it's important that we understand the equilibrium constant basically describes the ionization that we undergo. For water, we said that water can ionize to form hydronium and hydroxide. We said that neutral water, each of these is 10 to the minus 7. Equilibrium constant would be hydronium times hydroxide. Each of these are numerically 10 to the minus 7 molar, or Kw here is 10 to the minus 14. For a regular acid, something like HCl, the equilibrium constant would be hydronium, chloride, and HCl. Water's a liquid, it doesn't count. So this is what we would have. Because this is acid ionization, the convention is that we will call this Ka. So instead of Kc for concentration, we call it Ka. And for a strong acid, Ka is very, very large. What that simply says is, for a strong acid, you have lots and lots of hydronium. Ka is very, very large. If we were dealing with something like the organic acid, acetic acid, now this is the acidic component of vinegar. We have a CH3 group, this carbon-oxygen double bond, and our OH. This ionizes to form what we call acetate anion and hydronium. Products over reactants. For this, the Ka is very, very small. And this is a weak acid. Ka is very large, strong acid. Ka is very small, it's a weak acid. For acetic acid, I actually have the number here. This equilibrium constant is 1.8 times 10 to the minus 5. Again, a very, very small number. Almost no hydronium, mostly acetic acid in solution. Instead of dealing with numbers like this, as you recall, the convention is that we take the negative log of this and we call that a pKa. pKa is how we'll describe acidic carbons and things like that. The pKa here is 4.7. The rule to remember, the smaller the pKa, the stronger the acid. The larger the pKa, the weaker the acid. Nice, simple rule. These are some common acids. Again, this is acetic acid. We just looked at it. pKa of 4.76. HCl all the way down to -7. Smaller the number, the stronger the acid. Up here, HCN, water, ethanol, 15, 16, whatever. Large pKa, very weak acid. When we speak of the acetone anion, we've done the resonance form. The acetone anion has a pKa of about 19. So it's a very, very weak acid. Nonetheless, it's very important for the reactivity. Organic acids. As I said, alcohols can ionize. Again, lose the OH. Here's the anion. pKa of about 15, 16. This is acetic acid again. Form the acetate anion. We saw this is resonance stabilized. pKa about 4.7. And here I've spoken to about 3 or 4 times acetone anion. Here it is. Here's the resonance forms. pKa 19.3. Strongest acid, weakest acid. Any question? Okay, there's one more bit of general chemistry review we have to do, and that is to talk about Lewis acids. Yes, this is the same Lewis that drew the dots. Lewis devised his own acid-base theory that's actually much, much more general than the Bronsted theory. Bronsted was just proton. Lewis said, A Lewis acid is anything that can accept an electron pair. A Lewis base is anything that can donate an electron pair. Now we would look at a Lewis base this way. B stands for base. And all we're saying is that this has an orbital with a pair of electrons in it. It can donate that electron, or those electrons, to something. Therefore, it is a Lewis base. Anything that has an empty orbital can accept electrons. This could be metal ions. The example we'll use is boron. Has an empty orbital, can accept electrons. It is a Lewis acid. Specific example, boron trifluoride. This is a compound that we use in organic. This stuff is very unstable by itself. Why? Because boron is a group 3, isn't it? It only has 6 electrons around it. Very unhappy. This makes boron a perfect Lewis acid. Big, empty orbital. This is dimethyl ether. These oxygens, or this oxygen, has 2 unshared pairs of electrons, doesn't it? That means that this is twice over a Lewis base. It can be an electron donor. When you want to use BF3, what you do is you dissolve it in dimethyl ether. Why? Because we get a combination of these electrons into this empty orbital, and we wind up with this complex. This is a coordination complex, but it stabilizes the BF3 so that you can store it at whatever. Electrostatic potential maps. Here's our boron, big blue hole. Poor guy has no electrons. Here's our dimethyl ether. We have electrons here, and this is our complex. Any questions? All right, let's do one more thing here. This one's fun. These are intermolecular forces. Now, this is actually a movie that I captured of a real-time computer simulation. Intermolecular forces. The basic phenomena is that every particle, every molecule, everything has an attraction towards everything else, an inherent attraction. In this little computer thing, again, this is all calculated. It's like billiards. We're going to launch this guy at this pile of particles, and they're going to break apart. But what I want you to watch is what happens as they disperse their energy and bounce around the room. So there they go, just having a good time bouncing into each other and the walls. Slowly they're losing their energy. But now watch what happens. See, as they get close to each other, they start to stick. This is the phenomena of intermolecular interactions. Particles bounce off each other, but they have this inherent attraction, and eventually they will coalesce. Now, the number one intermolecular interaction we already talked about. That's hydrogen bonding. Hydrogen bonding is very important in organic chemistry. The types of hydrogen bonds we talk about, this is an NH, this is an oxygen. Again, this is our hydrogen bond. Here are two molecules of methanol. Not as good at it as water, but again, we have hydrogen bonding, and we can make extended complexes. Hydrogen bonding shows up lots of different ways. The three champions of hydrogen bonding are water, so that's OH. This is HF. HF is very good. NH. And down here is poor methane that doesn't hydrogen bond at all. This is a plot of boiling points. And what this is designed to show is that the more efficient we have hydrogen bonding, the stronger these things are held together, the more energy you have to put in to move them to the gas phase. Now this is the number one. There are other types that are much, much less, and most organic molecules exhibit those. This is induced dipole. Here we're going to take just two little balls. Let's pretend they're argon. We're going to put them next to ions. The reason that these particles stick together is that as they get close to things, we can get a polarization of the electrons so that they look something like this. Turn from our beautiful little spheres into eggs. And here we have a partial negative bonding here, partial positive bonding here. It's an induced dipole. Now, induced dipoles might seem like they're, kind of esoteric, but that's actually very important, especially for fish. Water is a very nonpolar molecule. It is hydrophobic. You would not expect it to dissolve in water. Again, that would make fish very unhappy. But the reason that it does dissolve in water is this induced dipole. We know that this is a partial negative spot. This is oxygen. What happens is we basically distort the electron cloud, drags it into water, hence the fish can breathe. Another classic example. When I was a child, if you injured yourself, parents had this weapon that they used on you called iodine solution. Don't use it anymore because it was just cruel and unusual. Basically, it was alcohol and iodine. This is electrostatic potential map of ethanol. This is iodine, I2. If you dissolve these two together, this is nonpolar, this is very polar. Nonetheless, they dissolve, makes this purple solution. And the reason is we get this induced dipole from the iodine and the ethanol like this. And you pour this on a cut, it's mostly alcohol, and it hurts like mad. Oh yes, those were the days. We can also go all the way here. This is called a dispersion force. This is the one that most organic compounds utilize. In a dispersion force, we have two totally nonpolar hydrophobic thingies that are just sitting next to each other, kind of like our little billiard balls. The reason they stick is that these electron clouds can undergo spontaneous polarization. They realize they're next to each other, the clouds reorganize so we have a positive and a negative end, and they attract. Now for an organic molecule, this is referred to as a van der Waals force. Again, these are simple hydrocarbons, totally nonpolar, and yet they will stick together. They stick together simply because we have these induced dipoles everywhere that these molecules touch each other. Very nice demonstration of this. This is the one we just saw. This is pentane, 5 carbons. This is called neopentane. Same 5 carbons, just arranged differently. You'll note we have a larger area for interaction here than we do here. This boils at 36, and this boils at about 9. The difference simply, same number of carbons and hydrogens, the difference simply is we have more interactions here than we do here. Just like we did for hydrogen bonding, as you add more and more carbons to a hydrocarbon, boiling point goes up, methane's down here, this is our 1, 2, 3, 4, this is butane up here, and it pretty much continues. Waxes, high boiling, high melting, those are just very, very long chains that just stick together. Okay, let's go ahead and do that. Work on the front page for about 5 minutes, then we'll go over the answers. And let me see who called me.
Bless you.
You know, it's very rude to have a cell phone go off and let everyone knows that. But I have 4 kids too, so I can't be a jerk about it. I can't. I'll just try to make sure it doesn't happen. Oh, right. Well, you weren't.
Oh,
I
yeah.
didn't add you to lunch. Okay. So you should be able to get into lunch. I don't need to do that. You just need to talk to whoever does that over there.
Okay.
I have no clue.
You just gotta go to
You ask
registration.
C,
But just make sure that they know that you're in the class.
G, D, V.
Oh, the welcome sign, and just go right there, they'll direct you. Okay.
Would you do for 9? Would you do for 9? Oxygen, negative. B.
Now I will tell you sort of the truth here. These questions, especially well, the ones, not the resonance ones obviously, these are taken from the database that will show up for the extra credit.
Carbon.
Okay? So now the database is large, so this is just a sampling.
Carbon's got it.
But these are the types of questions that you're going to be looking for. Remember, the extra credit must be done by tonight, unless you can. So please remember to send me something, and I'll try to set something up for that.
Professor, how long does it take to be added to the roster?
How long will it take to be added?
I just signed over this one yesterday.
I'm sorry?
I just signed over this one yesterday.
Oh, you did? You need to send me an email. bm@usc.edu.
But it says how many bondings.
Did you teach him 112 and 101?
Absolutely. Really?
Yeah.
So, anyway, send me an email.
Yeah.
And,
This says 9 and then that's not
I will
bonding.
add you manually.
I always
Make
do
sure
that.
that you go to Blackboard. On there, you need to download the syllabus, download the lecture slides that you don't have.
Yeah.
And remember, we have lab tomorrow.
Do you have to get a new manual for that?
I just,
Yes. It's, well, it's on the syllabus, but
Nah,
this is the lab manual.
for me.
And as far as the textbook goes, the book that is recommended for the course is McMurry 8th edition. However, that's very expensive.
No,
Anything
this
from the
line is
6th edition up will work. 6th edition you can get for about $15. Yep, and you need those.
Thank you.
All right, let's look at these.
Yeah, you're right. I didn't get that.
Any species that can accept an electron. What are we going to call that? If it accepts an electron,
C.
it is a Lewis acid, isn't it? A bond between two atoms differing in electronegativity.
Polar covalent bonds.
That's going to be polar and it's going to be covalent.
You know what's funny, because in the book, when I was reading it,
It says
it says protons, so I got confused between the protons and electrons. That's all.
A proton, if something accepts a proton, it's a Bronsted base. If it donates a proton, it's a Bronsted acid.
Right? So, yeah. So then the question said, any species that accepts an electron, so that would
A,
be
C,
the
Lewis.
Lewis
Right.
acid, which is
A, C.
C, right?
What do we call water-loving species?
Okay, he said A.
Hydro is the first word. For loving, we will use philic. Compound that can donate a proton, speaking of that. Different type of an acid-base description. This is a Bronsted acid.
DC.
Ability of an atom to attract shared electrons.
The lower.
This, of course, is simply electronegativity. Term used to describe water-fearing, water, hydrophobic. If we can donate electrons, if this is a Lewis acid, this must be a Lewis base.
I got it right. I'm sorry. I thought you said A for the first one. So.
And finally, if we can accept a proton, Bronsted acid donates, Bronsted base accepts. Any questions on these? All right, let's look at this. This is the amino acid phenylalanine. We are looking for, first of all, formal charges on the oxygen or wherever. It doesn't say. Any formal charges on these atoms.
B's got a negative.
Let's look at A here, as A comes first in the alphabet. Oxygen is group 6. Here we have 1, 2, 3, 4, 5, 6. It's neutral, right? B. Oxygen is group 6. We have 1, 2, 3, 4, 5, 6, 7. It's a -1. Nitrogen is group 5. We have 1, 2, 3, 4. Therefore, it is +1. You could also remember oxygen with one thing attached is negative. Nitrogen with 4 things attached is positive.
What about the carbon-carbon bond?
Carbon, look at any of these carbons. Carbon comes in with 4 electrons, group 4. These are all bonded up for 4 different things, therefore they're all 0.
Well,
This little asterisk here, you don't know what this asterisk means. That indicates this is a, quote, chiral syndrome. We'll talk about that in chapter 5. All right, oxygen labeled A has how many non-bonding electrons? Well, that's silly, you just have to count to 4. And oxygen B has how many bonding electrons? Well, these are all non-bonding, so we have 2 bonding electrons. Any question? All right, polar covalent bonds. Look at fluorobenzene. You can just look at your periodic table, or if you remember that fluorine is always the most electronegative element. So it's always going to win, isn't it? That means that this fluorine is going to be partially negative, and the carbon next to it will suffer and be partially positive.
You know,
This is going to generate a dipole, isn't it? With the positive end down here and the negative end up here. This is called furan. It's a cyclic ether. Tetrahydrofuran, actually. Tetrahydrofuran. Oxygen. If you look at your periodic table, oxygen is closer to the corner than carbon is, isn't it? So it's more electronegative. So that means that this oxygen is going to be partially negative, and that the carbons attached will be partially positive. Each of these is going to generate a dipole, right? So the dipoles will combine, we'll wind up with a negative end down here and a positive belt across the middle. Tetramethylsilane, TMS. We use TMS when we do NMR. Unfortunately, we don't have an NMR here. I'd love to buy one. But we look over here. Carbon is above silicon, isn't it? Remember, we said our trend. As you go up, electronegativity increases. So carbon is more electronegative than silicon. So that means, looking at just one of these guys, silicon is going to be partially positive. The electrons are going to be down here by the carbon. That's going to generate a dipole from here to here. But remember, because we have 4 methyl groups around this thing, we actually have 4 dipoles all pointing out equally. So this is a non-polar molecule tropy. Because you have 4 pointing out and they're all the same. These guys are polar. This one is not. And finally, let's do resonance. Oh no, this is acid base. This is our. Look at this equation. Which of these is the strongest Bronsted acid? Remember what we said about pKa's? The lower the pKa, the stronger the acid, right? We have 2 acids in this equation. This is called tert-butanol, tert-butyl alcohol. pKa of the OH here is 18. Water is the acid for the back reaction, 15.7. Which of these is smaller?
D.
This is, water is our strongest acid. What's the strongest base? acid, the weaker the base. Okay? This is the strongest acid, therefore this is the strongest base. Oh.
Why wouldn't it be KOH?
Hydroxide, conjugate base of water. This is a stronger acid than this, so that means that this is a stronger base than hydroxide.
Trick question.
All right, look at these guys and let's pick out acids and bases, both Bronsted and Lowry. Let's do acids first.
HCl.
Can methanol be regarded a Bronsted acid?
No. It has an alcohol.
Wrong. I like saying that. What does a Bronsted acid do? It donates a proton, right? Does this have a proton it can donate? Yes.
Hydrogen.
How about cyclohexanone?
Yeah.
Does it have a proton it can donate?
Not really.
Not really. How about HCl? Well, that one we all got right.
Yes.
BCl3. That has no protons, but it has a boron. What do you remember about boron? It's a Lewis acid. This nitrogen has a lone pair of electrons here, doesn't it? Doesn't have a hydrogen though, so it's not an acid. And finally, iron-free bromide. Metal ions are very good at accepting electrons from things and forming complexes. This is called a Lewis acid. We'll actually use iron-free bromide, aluminum chloride, in reactions as catalysts as Lewis acids. All right, how about bases? Can methanol be regarded as a Bronsted base? What does a Bronsted base do? It accepts a proton, right? Can we put a proton on there anywhere? Absolutely. Just like we can take water and make H3O, we can put a proton here, make methanol, protonated methanol, we'll just call it.
Sorry, did you say that's a Bronsted acid and base?
It's a Bronsted acid and a Bronsted base. Isn't that confusing?
Yeah.
Cyclohexanone, no protons, but the oxygen has lone pairs, doesn't it? That means it can be an electron pair donor. So it can be a Lewis base. HCl, no way. BCl3, no way. We have a lone pair here. We can donate that lone pair. Makes that both a Bronsted and a Lewis base. And finally, iron-free bromide, no way.
Sorry, HCl was a Lewis base.
I'm sorry?
Sorry, a Lewis acid, HCl.
HCl is a Bronsted acid. Because it's proton donor. All right, now everybody's favorite, at least my favorite. Let's draw resonance forms. This is a very important skill. Won't use it so much in 234, 235. We're going to do it like mad. Make sure you get it. This is a carbocation. Remember that there's a hydrogen attached here, okay? Always remember that. So it's a carbon bonded to three things. We could take this lone pair of electrons from the oxygen and we could move it from this center to this center to make a double bond. If we did that, that would neutralize this positive charge, but we'd have an oxygen bonded to three things. Remember our rule? Oxygen with three things is positive. Make sure you understand what we did. We just took this electron pair, we moved it in to make a double bond here. This carbon now has four things attached, so it's neutral. Oxygen, however, now has three things attached, so it's positive. All right, there's one more resonance form we can draw. We're going to do an entire chapter on conjugated systems. Conjugated systems basically are alternating double bonds. We could take this system here. Remember we started with a carbocation here. We could take this electron pair, move it up. That puts too many bonds here, so we have to put these back on the oxygen. And what we've done is to leave this carbon with only 3 bonds. There's our first move, there's our second, and we now have our carbocation out here.
That's what I was trying.
Okay? Let's do one more. This is a carbon bonded to 3 things, and it has an extra pair of electrons. That makes it a carbanion, -1. Formal charge of -1. We could take this electron pair and we could move it up to this sp² center. So right in here. Now that would put 5 bonds on this carbon, right? Can't have that. One thing that we could do, however, is just to take these extra electrons and just leave them right on this carbon. We start with a carbanion, we end up with a carbanion. So our first move looks like that. Moving electrons in. Got to get rid of these. And we wind up with our negative charge here. This should look a lot like the acetone anion to you, shouldn't it? This part right here. All right, one more thing we can do then. What did we do with the acetone anion? Well, we took the electron pair that was next to our carbon-oxygen double bond, we moved it in. In order to do that, we had to move these guys out onto the oxygen. So, move it in. That would give us too many bonds. We have to move these out, and we get the oxy anion. In terms of using this to predict reactivity now, we can say in this molecule, we expect negative charge on the oxygen, negative charge on this carbon, and a negative charge on this carbon. That's how you use resonance to predict reactivity. Any questions? All right, don't forget your extra credit. Extra credit will not make you draw resonance forms because Blackboard is not that smart. But there might be questions about resonance forms. Make sure you understand.
So that's on the Blackboard.
It's on Blackboard, under course materials. Good luck.
Do you want us to turn this in tomorrow or today?
Oh, no, give those back to me today. Remember to bring your goggles and everything tomorrow, please. Just